Okay, so today we'll learn about the least square curve fitting method. So the curve fitting method goes like this: ki some data points are given to us. What we have to do, we have to find out a curve which best suits the given data points. Okay, that means we do not know the actual curve. We are only provided with some data points, and our task is to find the best curve which fits these data points. Okay, so this is actually we have already learned it in the probability part of our syllabus where we have done the least square curve fitting. Okay, so the idea goes like as below: key that these are the points which are sup- supplied to us. These are bivariate points. As you can see, there's this x1 y1 x2 y2 x and yn, so it is a two-dimensional point. Okay, n pair of such points are supplied to us. Okay, now our objective is to fit. Here they are saying a parabolic curve or a polynomial function of degree m. It is a specific one. It can be any curve. Okay, so let us study this one because the general procedure is exactly the same as we will discuss here. Okay, so now we fix our objective to fit a parabolic curve or a polynomial function of degree m. Okay, now if we consider a parabolic curve or a polynomial function of degree m, it should be of this form, right? Acha. Then of degree m, so this is the x to the power m is the highest degree term possible here, and these are the observed data sets which is given to us, and we have to compute the m plus 1 constants pj. So the thing is that this we have to fit a curve of this form, but here these pi's are unknowns. So once we know these pi's, or once we derive the values of these pi's, this curve becomes known. So that is our main task here. Our task, as we said, key we have to fit a curve which best suits this data points. Okay, so we have to find out a curve of this form, but which pi's will be the best candidate in this case, that we have to find out. Okay, so let us have this picture clear in a geometrical way. So these red dots are the data points which are given to us. Okay, and this is the curve which we are trying to find out, the curve of best fit. Okay, acha. So I just name it as a gamma as the curve which has to be fit here. So the curve is, I'm taking that form which is given there, y equal to summation over pi xi. That means the polynomial curve I am taking. Okay, where pm obviously non-zero because you are saying a curve of degree m. Okay, and these are the points, the observed values given to us. Now you see, if it was the case ki xi yi or xj yj, any of these points was on this curve, suppose, then what we can do, we can say that that point will satisfy this curve. That means we can say something like this: ki yj equal to capital Yj here equal to summation over pi xj to the power I. If xj yj is lying on the curve, this curve, then we can say like this. But actual scenario is what? We do not know whether xj yj lie on gamma or do not lie on gamma. So in general, the small yj not equal to capital Yj. So as soon as small yj not equal to capital Yj, take any point. Say I take this point, x1, y1. And corresponding, if it was on this curve, say this was the point or any point here. So what can we do? We can find out the distance between the small yj and the capital Yj. Okay, we can find out obviously because these are 2 points. We can simply find out the distance. Okay, now we are trying to find out the curve of best fit. Okay, so the curve, which curve will be the best fitting? That curve for which this distance is the minimum for every j you consider, that means for every observed data point. Okay, so this is the motive of construction of the curve of best fit. That means we do not know whether these observed data points lie on the curve which we are assuming. Okay, so we will choose the curve in such a way so that this distance between these actual points given to us and the points which we should get if we assume that the points lie on the curve we are taking, that means capital Yj, this means distance is the minimum. That curve, corresponding curve, will be our curve of best fit. Okay, and this should be holding, this minimum thing should be holding or checked rather for every data point. It may happen if for some data point you are getting some yj and for another data point you are getting another yj, so that won't be the case. Okay, so as to avoid that type of complexity or so as to avoid that type of error, what we take the summation of all this. summation over all of the data points. We are taking n, small n number of data points. So we add up all these squares. Okay, so yj minus capital Yj minus small yj whole square. We take the adding or sum of all this corresponding to all the data points. Now, as I am saying repeatedly, this should be minimum for all j. So definitely, if this is minimum for all the data points, so there obviously the summation should also be the minimum. So this is the thing. This is the main basis of this least square curve fitting thing. Okay, and this has a specific name. This whole square thing has a specific name. It is named as a residual for the jth observed value. Residual means this what actually is given and what it should have been taking the form if it was on the curve which we are taking. Okay, so this thing and this capital S, we are taking nothing but the sum of the squares of the residuals. Okay, so this thing Rj, we are taking like this. We have sum of the squares of the residuals. There is this typo here. There won't be any square in this part. Rj equal to only the difference in between these two. So capital S turns out to be sums of squares of the residuals. So there will be no square in this part. Okay, only the summation over k to 0 to m pk x to the power k minus yj. Only this thing is the residual. Okay, so the gamma is the best fit curve when S is minimum. Now you see, as I already said, ki gamma, what is unknown about gamma? X and Y, here if I go back to the form of the gamma, you see Y and x square, everything obviously are just running variables. Okay, so what are the things which is parameterizing this curve? These are the PIs. Okay, for example, if you take the curve y equal to 2 plus 3x plus 5x square, then that is a parabola. Again, if I take y equal to 2 plus 5x minus 10x square, again that is a parabola. But these two parabolas are different because the coefficients are different. Okay, so these PIs are the thing which will tell us which curve you are going to take. So everything now depends on what this PI is. So what the minimum which we are trying to calculate here should be the minimum with respect to these parameters. Okay, so S is to be minimized over these parameters P0, P1 up to Pm. Okay, if it is a parabola, then only 3 P0, P1 and P2. Okay, so del S del Pi equal to 0. This is the, we know the strategy for finding out the critical points for the minimization procedure, and these are named as the normal equations. Okay, so if the here the number of variables is m plus 1, so you will get m plus 1 normal equations, and the number of unknowns is m plus 1. So from m plus 1 equations, you can simply just find out the m plus 1 unknowns, unique values, because the number of equations is equal to the number of unknowns. So you will get the unique values. So once you get those values, you know the curve gamma, and that is the requirement to find out the best fit curve here. So this is the procedure which we will be going to follow here. Okay, so once this idea is clear to us, let us come back to the formal approach which they are taking here. So this, as we already said, ki S is a summation over Ri square. This is Ri is the residual. Residual means this thing. Ri square means this whole square thing. Okay. Achha. The therefore by the virtue of the principle of least squares, S is minimum. Okay. For which the m plus 1 normal equation turns out to be like this. Now once you solve these equations, they will take the forms. For example, I just consider del S del P0. This is only for the calculation part only. If you just check it on your own, del S del P0, if I want to do, then that means you are trying to differentiate partially with respect to P0. Which one? This capital S. Capital S means this one. So this, you just simply follow these steps and you will get for del S del P0, this turns out to be this quantity. Okay. This is simple because just keep one thing in mind. Here these xi's are not our variables, the yi's are not the variables, only the p0, p1 and pm are the variables. Just keep that thing in mind. Okay, then this calculation is very trivial. So yes, I have just broken this sum term by term, and then I'm applying the del p0. Obviously it is a linear observable, so it is to be observed. It is to be just applied over each and every one of this summation terms. So I am applying them, and then I am just showing one at a time. Pk k term I am showing from here, not k, for example jth term. Okay, So if you take the jth term, I'm just showing it separately so that it is better, easier to understand. If you just do like this, you are going to get this one. You are differentiating with respect to p0. So once you get this term, along with it, 1 will be multiplied because there is nothing other than the 1, the coefficient of p0. Okay. So this is it, and this is true for every j you are taking. So you just can find out and plug it in here. So once you plug it in here, you will get this expression. It will be better if you check it on your own. Okay, I'm just giving the hint. So del s del p0 equal to 0 will ultimately give you this form. Similarly, for any del s del p j or del s del p t, where t is running from 0, 1, 2 up to m, you will get anything like this. This is in general. Xz to the power t will be coming depending on which t you are taking. If you are taking p0, say xz to the power 0, that means 1. That's what we have got here. If you are taking p1, then it will be xz term multiplied with this thing, and likewise. Okay. So adding up all this, in general, you will be getting these equations. This one, this one, this one, and up to in m plus 1 equations. Okay. So now you see what is so special about this thing. We are trying to find out the pi's, okay, and xi, yi are given to us. So if I just concentrate on this equation, this part is known to us, n is known to us, p0 unknown, p1 unknown, again summation over xi, summation over xi square, and everything relating to or using xi and xyi, any function related to xi, yi is known to us. So only it is a linear equation in p0, p1 up to pm, similar for the other m equations. So you are generating a system of m plus 1 linear equations in n plus 1 unknowns. So you can just easily solve to find out unique solution. Uniqueness is very important because we are saying we are finding out the best fit curve. It cannot happen ki you are finding out two best fit curve at the same time. Okay. So the things goes like this. So using the normal equations, you can just simply get this type of form. Okay. So they are now treating specific cases. M equal to 1, you get linear curve. M equal to 2, you get a second degree parabola. And some other curves, as I said, you can also do that. Say I take a equation, I want a curve of this form, y equal to px to the power q. Okay. Then what you have to do, you can just simply see it will get converted to one of our known forms via this logarithm operator. You are taking log on both sides, log to the base 10 if you take. So this turns out to be this one. You just simply take this a, y, capital Y equal to log y to the base 10, capital A equals to log p to the base 10, b equals to q, and capital X equals to log x to the base 10. Once you take this, it gets converted into y equal to a plus b. Now again, this is a linear form. So you can just simply take this, apply the residual method, find out everything. So finding out everything will allow you to bring this form. Once you can bring this form, then using this relation, you can revert back and put everything here to get this form. Okay. Similar for the y equal to p into q to the power x forms. Again, you have to take the logarithm so as to convert it into linear form. Just apply the method which we have already learned, and then just plug in into the main equation using these relations. Okay, so as to get this type of form. Okay, and related to this curve fitting thing, there is a measure of estimate, you may say, a goodness of fit. A measure of goodness of fit of the best fitting parabolic curves is given by this formula. This formula is nothing. They are using these residuals, 1 minus summation over r by yi square, the residual corresponding to the ith variable or the ith data point, not the ith variable, but the ith data point. Okay, and this run over all the data points provided by n into summation sy square, where sy square is this thing. There is the marginal variance. You already know this thing from the statistics part. Okay, so this thing where capital N is the number of data points. Here it should have been small n because we are using small n all over. So whatever the number of data points here, it should be taking. Okay, and capital summation over ry square is taking this form. Okay, so this is it. For any curve fitting, you can calculate this thing. Okay, so this ends here.